Now that we learned about the linspace, let's take a look at one cool application here. Suppose we want to find a solution for the following quadratic equation. We have x squared minus 5x plus 6 equal to 0. How do we use np.linspace to help create and find a solution for this quadratic equation? Let's take a look at this line of code. Set candidates to be np.linspace, and the starting value is -1000. The terminal value is 1000 with 2001 number. For candidate, in the candidates, what it's going to do, if candidate raised to power 2, it's basically saying that, hey, x squared minus 5 times the candidate, or minus 5x plus constant 6. If you plug in the candidate and the result is comparable to 0, it's going to print just found a possible answer. So please pay attention here why we are selecting -1000 and 1000 and 2001. The total number of values between -1000 and 1000 inclusive is 2001 numbers. Well, in this case, when you're using np.linspace, it guarantees that you get numbers like -1000, -999, -998, or basically the integers between -1000 and 1000 with step size of 1. It generates the numbers or the solutions that satisfy this quadratic equation to be 2 and 3. Please note that if you use 2000 instead of 2001 for the total number of values that you want to have in between -1000 and 1000, since the spacing is slightly less than 1, you'd miss out the exact integer steps between -1000 and 1000. I highly encourage you to change this number to different values, and basically you see you don't get any solutions or x values for this quadratic equation. For those of you who are going to take linear algebra, I function is an important function because it creates identity matrix for you. The function np.I with parameter a in NumPy creates a two-dimensional or 2 by 2 matrix with ones on the main diagonal, and the rest of the numbers are going to be 0. The parameter basically specifies the number of rows, and this is the same as the number of columns because you have a square matrix. For example, if you run the following line of code, np.I, and pass in parameter 4, you get a 4 by 4 square matrix with only ones on the main diagonal. So again, for those of you who are going to take linear algebra or take in linear algebra, this function basically creates the identity function, which is a square function for you. Remember that both np.random.rand and np.random.randint are used to generate random numbers in NumPy, but they differ in distribution of numbers they produce. For example, if you look at the syntax of np.random.rand with parameters d0, d1, d2, d3, dn, it generates random numbers from a uniform distribution between 0 and 1. But the syntax for np.random.randn with parameters d0, d1, d2, d3, and so on, it generates random numbers from a standard normal distribution or Gaussian distribution when mean is 0 and standard deviation is just 1. So for example, if you run the following line of code, you get np.random.rand2. It basically generates an array of 2 random numbers. And if you take a look at the next line of code, np.random.randn with 2, it basically generates 2 random numbers. But as you can see, since it's taken from standard normal distribution, we expect to see negative values as well. If you take a look at np.random.rand, 5 and 5, you pass in 2 numbers. It basically gives you the following array of 5 rows and 5 columns. Again, taken from a uniform distribution. And if you just change this to randn, 5 and 5, as you can see, we have negative numbers as well because these values are taken from standard normal distribution. Next one is randint. The syntax for np.random.randint function in NumPy is as follows. You have a low, you have a high, you have a step size, and the data type. For example, if you take a look at the following line of code, np.random.randint between 1 and 100, it basically generates 97, which is a random number between 1 and 100. Of course, if you run this line of code, you get a different value. And basically here, I'm saying that, hey, I need 10 number between 1 and 100. It creates random integers in the form of an array of random numbers taken from 1 and 100. So these are different ways to simulate numbers deriving from NumPy and other distributions that basically helps us in simulation. Sometimes we have seed. Students asking, hey, what a seed is. In some, suppose you have a very long list of numbers written down in a notebook. Every time you need a random number, you open the notebook and pick a next number from the list. Then you close it. Without the seed, every time you open the notebook, you randomly flip to a different page and start picking numbers from there. Because you're always starting from a different spot in the notebook, you get different numbers each time. However, if you add a seed, instead of flipping to a random page, you use the bookmark page, which is basically they start from the same page every time you open the notebook and you want to select a random number from that same page. Why it is important to have a seed? So basically, when you're using a seed, when you're sharing your code, especially in scientific experiment or debugging, it's important that other people get the same result you did. Setting a seed helps everyone gets the same sequence of random numbers. And it's important for testing and debugging. If you encounter a bug or need to test the program, you want to ensure that the random numbers generated are consistent so you can isolate the problem and deal with it. For example, if you take a look at the following line of code, np.random.random3, we basically expect to get 3 random numbers, and it's in the form of an array. So this function basically generates a 1D array of shape 3 filled with random float drawn from a uniform distribution as we saw before. The next line of code is np.random.randint 0, 11, and 3. We basically get 3 numbers randomly taken from 0 and 11, and it's in the form of an array. And we discussed this in previous slide as well, just a good summary for you. So alternatively, we can basically take these numbers or generate these numbers from different types of distribution that we briefly mentioned. np.random.normal 0, 1, and 3 is basically saying that, hey, I'm setting the mean equal to 0 with standard deviation 1, and I want 3 numbers out of it. So if you run this line of code, for example, you get these 3 numbers in the form of an array or a vector. The next one is np.random.logistic. So here you're basically generating 3 numbers from a logistic distribution. In this case, you get an array of numbers taken from a logistic distribution. Another one that we mentioned before as well, just summarizing it, np.random.uniform 1, 2, and 3. We're basically generating 3 numbers using uniform distribution with the low 1 and the high 2, the minimum value and the maximum value. When we're talking about np.random.choice, it basically generates a 1D array line, and you might be interested in adding, for example, the size and replace true. So what does this guy do? It helps you to randomly select elements from a given array or list. It can be used to randomly sample from a 1D array or a list with or without replacement, and with customized probability from each element as well. Shortly, we're going to see how we're going to use .choice. So our focus is on simulation of random events. As you know, simulation is very important. For example, when you're dealing with uncertainty and risk. Risk analysis is one of the important part in finance, especially that we use simulation. Simulation can also help compute prediction intervals or range where future observations are likely to follow. It basically modeled the uncertainty in predictions made by machine learning algorithm and statistical model. So on the right-hand side here, you have a population which is not normal. It is basically skewed. And by taking sample means from the population, we basically create a normal distribution that we can apply confidence interval and also hypothesis testing on them. Here's how we can simulate the number of heads in 100 tosses of a coin using NumPy. First of all, import NumPy as NP. The next line creates basically a NumPy array named coin that contains two elements, heads and tails. The array represents two possible outcomes of single coin toss. The next line of code basically uses the NumPy function np.random.choice that we mentioned in previous slide to simulate 100 coin tosses. It randomly selects one of two outcomes like head or tail from the coin array 100 times. This result can be written as head, tail, tail, comma, head, or in other orders, depending on what you get in each toss of the coin. Finally, we have np.count underscore non-zero, and the outcome is comparable to heads. What does it do? It basically counts how many of those 100 tosses results in heads. So it works by first creating a Boolean array. It takes the outcome and compares it with heads, where each element is true if the outcome is heads and false when the outcome is tail. For example, when I run this line of code, I get 35. If you run this line of code, you probably get a different number. So since we want to stimulate this multiple times, what are we going to do? We basically define a function to simulate one set of 100 coin tosses and return the number of heads. So we define a function, one underscore stimulated underscore value. What does it do? It basically defines our function for us, and it set the number of coins, the number of, we take the coin and we toss it 100 times, and this is basically our outcome. So now we count the number of heads. To better understand the variability, we're going to simulate the process more times, like 20,000 repetitions. Each time we toss the coin 100 times. So when you set num underscore repetition to 20,000, this basically sets the number of times you want to simulate 100 coin tosses. Next, np.array, which basically initializes an empty NumPy array called heads, where we will store the number of heads from each of the 20,000 simulations. And now we have a for loop. This is basically a loop that runs 20,000 times. Each time it simulates 100 coin toss by calling one underscore simulated value value open close parentheses and append the result, the number of heads in those 100 tosses, to the head array. And finally, we want to find the length of the heads, or how many heads do we get in this array. And finally, we are interested in visualizing what do we have. What are we going to do? We're going to import matplotlib.pyplot as PLT, and we're going to label our histogram np.arange 30.5, 69.5, and 1. This is the number of beans that we're going to create here, and we're going to count the number of heads in 20,000 simulated for 100 tosses of the coin. And basically what you see, the average is around 49 to 50 or 48 to 50. This is the balancing point, and this is how we visualize our histogram. So pretty much a normal distribution of number of heads in 100 coin tosses.